today's section about classification with rare classes. When dealing with the classification problems involving rare classes, the primary challenges is that the minority class is underrepresented compared to the majority classes. This can lead to biased models that biased models that perform well on the majority classes but poorly on the minority classes. Here, a detailed guide on handling such situation along with the examples. Right here, the problem is the rare class classification. That means here the data set is belongs to imbalanced data set. That is the classes. If you consider the binary class data set, the binary class means we are having the zeros and ones, 0 and 1 as a class label. The count of the 0 and the count of the 1 should be equal. Then we can say that it is a equal database or normal database. If we have the count is differences varies like 0 equal to 100 and 1 equal to 10, then we can say that the data set is a imbalanced data set. Like that we have the different databases. Here we're going to discussing the problem. This occurs when one class has a significantly fewer instances than the other class. Already we said that we have the fewer instances in the particular class. The common examples includes fraud detection in a financial transactions, the fraud versus non-fraud transactions. That means in the bank we're going to transfer the amount, or we are going to be finding out the fraud detections. We are having the very less fraud detections, and we are having the more transactions. In that, we are only having the 10 or 5 frauds in the transactions. Another one is disease diagnosis in medical dataset, presence versus absence of rare disease. That we are going to be finding out the presence and the absence of rare diseases. In the same way, the spam detection in the email classification, spam versus non-spam. These are the different examples come under to the rare classes. Okay. Now we're going to see the strategies of strategies to handle rare class classification. In that, first one is data level approaches. In that, we're having the resampling techniques. That means the data set is coming under to the data level approach. In that, we're having the oversampling and undersampling and generating the synthetic data. That is, the oversampling means increasing the number of minority class samples. That is, if you are having the higher means we're going to get the oversampling. If you are having the lower, that is decreasing the number of majority class samples to balance the data set is commanded to the undersampling. Okay. In the undersampling, we're having the two techniques. One is smooth, SMOTE. We can say that synthetic minority oversampling technique and adhesive or adaptive synthetic sampling, that we can say the ADASYN. Right? It is an extension of smooth. That is, synthetic minority oversampling technique generates the samples for the majority classes by interpolating between the existing minority class samples. It is going to be increase or equaling the both the minority and non-minority classes. Adaptive synthetic sampling, an extensive of smooth that focuses on generating synthetic data for minority classes, for example, that are harder to classify. Coming to the undersampling. Undersampling reduces the number of majority classes samples to balance the data set. In that, we are having the two types. One is random undersampling and Tomek lines. Tomek lines. Randomly removing the samples from the minority classes. So we are going to be reducing. That means we are going to be removing the randomly whatever having the higher samples, majority samples will be reduced, or remove the samples that close to each other but belongs to different classes, focusing on the cleaning the boundary between the classes. We're going to be eliminating the different classes in the data set. Next, we're having the generating synthetic data. That is creating a new data set points to the minority class based on the domain. That is about the data level approaches, algorithm level approaches. In that, we are having the cost sensitive learning and ensemble models. Cost sensitive learning model is assigning the higher misclassification cost to the minority classes to p- penalize the incorrect prediction more heavily. That is, we are going to be cost instruments. We are going to assigning the higher misclassifying cost from the normal one. Enabling methods. In this enabling methods, we are in the two methods: balanced random forest and easy ensemble and balanced cascade. In the balanced random forest, modifying the random forest algorithm to balance each bootstrap samples. Right here, we're going to modify in the random forest algorithm to balance the each bootstrap samples. Whereas in the easy ensemble and balance cascade, iteratively train the ensemble classifiers on balanced subset on the dataset. That is, we're going to be iteratively we're going to be training the subsets. That is called the easy ensemble and balanced cascade. These are the two different methods having in the algorithm level approaches. And third one is evaluation metrics. That is each and every classification model having the some metrics like precision recall, F1 score, confusion matrix, ROC and AUC curves, precision and recall AUC. Now we'll see the what is the confusion matrix. Right, confusion matrix is to find the classifications of data. Confusion matrix is a performance evaluation tool machine learning representing the accuracy of classification model. It displays the number of true positives, true negatives, false positives, and false negatives. Here I consider some example of the identification of dogs and not dogs. In this, we have the predicted and actual. The predicted we have the dog, predicted and actual. So whereas we are going to get in the dog, it is a true positive, that is we call it as TP. Dog and not dog is a false positive. Not dog and dog is a false negative. Not dog and not dog is a true negative. That is, if you get in the dog and dog means true positive. If you got in the not dog and not dog means true negative. If in the positive, that is dog is identified as a not dog, then it is called it as false positive. Not dog is identified as a dog, then it is called as a false negative. Here we have the true positive. This is the total counts having the both predicted and the actual values are dogs. A true negative. The total count having the both predicted and actual values are not dog. False positive. It is a total count having prediction is dog while actually not dog. False negative. It is the total counts having prediction is not dog while actually it is a dog. That is about the confusion matrix. Now we will see how we are going to get the from the data set. We're considering the some data set. From that we're going to calculate in the true positives and false positive, false negative and true negative. Here we have the data set with the indexing 1, 2, 3, 4 up to 10. In that actual, we are having some data dog, 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 not dog, dog, not dog, 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 not dog, dog. And the predicted dog, not dog, dog, not dog, 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 and ninth one is not dog, and tenth one is not dog. Based on this, we are going to say that from the index one, it is a we are getting the both dogs. That is a true positive. We get in the dog and not dog. That is a false negative. If you get in the dog, dog means true positive. Not dog means true negative. Dog, true positive. Not dog. That is false positive. Dog, true positive. Dog, true positive. Dog, not. That is true negative. Again, we are getting the true negative. From that, totally we are having the count of actual count dog is equal 6. Here we are going to have the actual in that we are having the totally 6 dog count. Here 3, 4, 5, 6. That means remaining are not dogs are count is 4. True positive count. True positive count means 1, 2, 3, 4, 5. False positive count. That is FP. Only we have the 1. True negative. True negative 1, 2, and 3. False negative. Only 1. That is the second index. Right? Now we are going to be giving the values to the true positive like this we're going to get, and we're going to calculate in the accuracy. Right, true positive we're going to get the 5 based on the above table. False negative equal to 1, false positive equal to 1, true negative equal to 3. Here we have the performance metric formulas like accuracy, precision, recall, f1 score, and specificity. So true we're going to calculate the accuracy, that equal to TP plus TN by total. That is TP plus TN plus FP plus FN. Here we have the TP is 5, TN is 3. So the total is 5, 6, 7, 8. 8 by overall. That is 10. So we are going to get the accuracy. Precision equal to TP by TP plus FP. TP equal to 5 by 5 plus FP equal to 1. That is 6. 5 by 6. So we are going to get the value. Recall equal to TP by TP plus Fn. The TP is 5 value by 5 plus Fn equal to 1, 6. F1 score equal to 2 into precision into 2 precision into recall by precision plus recall. That is, we are going to get in some values in the precision and recall. We are going to substituting that values in the wherever we have the precision. We are going to be substituting the precision value at the place of recall value, so that we can get the F1 score. Simply specificity equal to true negative by true negative plus false positive. True negative is here we have the 3, 3 plus 1, 4. That is 3 by 4. We are going to get the specificity. And we are having the ROC curve. Right? The true positive rate is a synonym for the recall, and there is therefore the definition as follows. TRP equal to TPR equal to TP by TP plus Fn. That gives the true positive rate. Here ROC means receiver operating characteristic. Under we can say that area under curve. It measures the trade-off of between the true positive and the false positive rates. So we have to draw. We are going to be generating the graph between the TPR and FPR. That is true positive rate and the false positive rate. The formula for the TPR equal to how we are going to get means TP true positive by true positive plus false negative. For the false positive rate equal to false positive by false positive plus true negative. These are the formulas we are going to be using to generate the graph between the TP rate and the FP rate. This is the graph we are going to get in the 0 to 1 and 0 to 1 in the FP and TF. Here we are having the TP vs TP rate and the decision threshold. Here we have the some threshold. Again here we have the one decision threshold. There is a final. Based on this, we are going to be saying that. Based on that, we are going to saying that we are having the graph between the TP rate and the FP rate. Next, we are having the area under curve. Under the curve, whatever we have in the shade, it is called the area under curve. This is about the evaluation process of metrics. And here we have the data presentation. Here we have the data presentation, data preparation. Here we're going to consider the code for the Python to prepare the data. Here we're going to importing the pandas as PD from sklearn model selection import, training, test and split. Importing the imbalance data set so that we're going to import in the smooth so that for the from imlearn dot over sampling import smot smooth. For imbalance under sampling import random under sampler from imlearn dot pipeline import pipeline. Now we're going to be loading the data set, that is the credit card fraud detection data set. We're reading that print data. We're going to be displaying the information of the data set. After that, we're going to consider x equal to data dot drop class x is equal to 1, y equal to data of class. Now splitting the data into the training and split data by using the x underscore train, x underscore text, y underscore train, and y underscore text equal to train underscore text underscore split x comma y comma text underscore size equal to 0.3 random state for 42 or whatever it may be, we can take the any number and stratify equal to s. Now we're going to check class distribution, that is we're going to printing the y train count. And next we're going to do the resampling. Here we're going to define the resampling method, that is smooth equal to random state equal 42. Randomly it is going to be generating resampling training data, that is x underscore res y underscore res equals smooth dot fit sample x train comma y train. Ash check new class distribution. We're going to be getting the new classes. That is it is generating the new class, that is resampling, that will be printed. Uh, that is y underscore res resample dot value underscore count. After that, we're going to be training the model. For that, we're going to using the random forest classifier, and we have to find out the classification metrics, performance metrics. So that for class for from sklearn, we're going to import in the metrics, import class report, confusion matrix, ROC curve. All these we need. And now initializing the classifier model equal to random state equal to 42. Now we're defining that training the class so that model dot fit x res resampling comma y resampling. Predict on the test set. We're going to predict y underscore predict equal to model dot predict x comma text. For the model, we're going to give the text data set to evaluate the model. Evaluate the model. Print confusion matrix y comma y underscore text comma y underscore predict. Print classifier report y underscore text comma y predict. We're printing the ROC curve score y underscore text comma y predict. For this, we're going to get the classification metrics as well as the ROC curve. I hope that you understand that how you're going to be importing the model and importing the metrics and calculating. Now we're going to calculate in the cost sensitive learning. In that, we're going to from the ensemble models we're having the importing the random forest classifier, initializing the cost so model equal to random forest classifier of class weight equal to balance, comma random state equal to 42. We define that here the random state equal to 42, so that here also we're going to take in the 42. Train the classifier. So model dot fit x train comma y train. Predict on the text set. We're going to predict in the text set y predict equal to model dot predict the x comma x underscore text. Evaluate in the model.